Or-
And so, how is everyone this evening?
Oh, it's really hot in here. Yes.
Hot? Oh yeah, you in the
In the valley,
you in the
yes,
valley?
sir. It's like scorching hot. And then,
It,
yeah. And then,
it's
uh-huh.
pleasant near it's pleasant near the beach here.
One other thing is that, my landlords like to watch television, and it's very
Yeah.
difficult to stay away from the noise. So I'm wearing this ear muffler. So it's a
Yeah.
classic studying difficulties without having library access.
Yeah. Good evening, Masood.
Hello?
Hi,
Masood?
Professor.
Oh yeah.
Yeah. So everyone's
Okay.
here. Now, I allowed annotations so you can scribble on my whiteboard, all of
Yes.
you, if you want to.
Thank you.
I think I did.
Yes. Let me see.
So let's start with questions.
Yes. On page page 117, the total variation of f should be big letter F, capital F.
Yeah.
And then on page 119.
Yeah.
So toward the second half, there's that
Yeah.
F plus plus F minus for the absolute value.
Yeah.
Yeah, so we have this F is equal to F plus plus F minus. Kind of the same idea, I guess.
Yeah.
And then hence there's a line below it that hence TF less than equal to PF plus NF. So if we do the supremum, then and then do the common refinement, then wouldn't it be just equal sign and then we're done with it?
No.
So
not quite.
Not quite. Okay.
Because if you do, you have to essentially what you have. Let me get my pen out. You have this summation j equals 1 to n absolute value ftj minus ftj minus 1 equals the summation plus the summation minus, right?
Yes.
Right. Now, what you do is, this is less than or equal to supremum summation plus plus supremum summation minus. The problem is that this supremum might be approached, but might be closed by a different partition than this supremum.
Right.
Or the supremum on the left. So you have to take all three suprema separately.
Right.
And then if you take at the end the supremum on the left, what you get is that you just get this. Tf of x is less than or equal to pf plus nf.
Oh, I see.
Because you can't just take the supremum over all partition on both sides.
Ah, okay.
You have
So
to take
inequality.
the
Uh-huh.
suprema separately.
I see, I see. And then inequality still holds valid.
Right.
Ah, okay, okay. I got it.
But
Next, yes.
Oh, sorry. Can we go back to 117? I had a question on there.
Yeah,
Okay.
you can go back to 117.
For 117, on example 2, it says f prime is bounded. What do they mean by f prime, the derivative?
Yes, it
Okay.
is the derivative.
Okay, okay.
And then the inequality you see there comes from the mean value theorem.
Mhm.
Okay.
Okay. Now, the whole section is in one dimension because, first of all, the mean value theorem is used, and in several dimensions, we don't have the mean value theorem because our domain is not an ordered set anymore. And but yeah, they mean the derivative.
On the page 120,
Yeah.
the proof of theorem 3.3 that
Yes.
uses that each fj is bounded and increasing. So
Mm-hmm.
I understand that fj needs to be bounded, but then why do we need increasing?
Well, theorem 3.3 says that's what we want to prove, right? 3.3 says that a real valued function on interval AB is a bounded variation if and only if f is the difference of two increasing bounded functions.
Oh.
And so that right?
Yeah.
That's what we want to show.
Yeah. So the statement requires it, but why do we require increasing?
Okay. Now, there's maybe something first we should say. If f and g are of bounded variation on an interval AB, so this is the set of all functions which are of bounded variation on this interval BV of AB. Okay, and this is a vector space. That is easily seen, right? Because AF plus BG is also a bounded variation. That's all we have to show.
Mm-hmm. Mm-hmm.
Right. And so the theorem is an if and only if theorem.
Yes.
And so the first sentence is if F1 and F2 are bounded and increasing, then F1 and F2 are both of bounded variation.
Mm-hmm.
And this implies F1 minus F2 is of bounded variation.
Mm.
So the increasing functions, they do not form a vector space because you can't subtract.
Right.
And even if you generalize it to all monotonic functions, they don't form a vector space.
Mm.
But bounded variation does form a vector space. So that's why you can do that. So that's the if direction of the theorem. The only if direction is this, the two sentences starting with conversely, suppose f is of bounded variation, and then they put f1, they define what f1 is, and f2. Now f1 is p of a comma x plus f of a. Well, the f of a is a constant, that doesn't matter. But p of a comma x is clearly an increasing function in x.
Because you're lengthening the curve. Is that
If
why?
it were a curve, you would lengthen the curve.
Yeah. Okay,
Right.
that kind of makes sense. Yes.
But if you just think as a regular graph, you increase basically the possible variations. Okay, and so is n sub f of a and
Yes.
x.
Yes.
This, by the way, was a problem on recent comprehensive exams.
Oh, thank you. we need that
Showing that
vital information.
Or at least one half of that thing, showing that if f is of bounded variation, then f is the difference between two monotonically increasing functions. By the way, you could have a different theorem here. You could have the same thing. Well, first of all, if f is monotonically decreasing, and bounded, then f. Then f is of bounded variation. That goes exactly the same way as example 1.
Yes.
It's just the opposite. You don't end up with f of b minus f of a. You end up with f of a minus f of b. And second, if f are bounded and decreasing, you could show that just the same way.
Oh.
So it's the increasing part is really not that critical. The critical part is that the two functions have to be
same direction. Same direction.
Of the same kind.
Okay. I see. Excellent.
Now there's an interesting aside here. In 450A, in advanced calculus, you learn that if f is an increasing function or decreasing function, if it's monotonic on the interval AB, then there is at most countably many discontinuities. Does everyone remember that theorem?
I remember seeing that somewhere. Yeah, it's in the Rudin chapter continuity 4.
It's actually not a hard thing, because if f is increasing, the only way it can be discontinuous is that it jumps up, right? That the limit as x goes to x naught minus of f of x is less than the limit as x goes to x naught plus of f of x. It can't have any of these funky discontinuities like sine 1 over x. And that means there is a gap there. And every gap has to contain at least one rational number. And that means you can label the number of gaps by the rational numbers, and so the rational numbers are countable, and therefore you have only countably many gaps.
Oh.
I mean, this is a very simple proof.
Oh my goodness, this is so easy to grasp and memorize.
So to show that this is the only possibility of a discontinuity, though, is a little harder.
Oh.
But it can't have. But
is it because the domain is compact?
It doesn't have to have compact domain. There's no reason for that. But the discontinuity of the second kind cannot happen for an increasing function.
Ah, okay.
The topological sign discontinuity, that can't happen.
So it's increasing or decreasing, right?
Yeah, increasing or decreasing. Well, that tells you that if f is of bounded variation, well, it can still only have countably many discontinuities.
Oh. Oh.
Well, the object of this section is
differentiability.
That if it's a bounded variation, then it's differentiable except on the set of measure 0.
Oh. Okay.
Which could be uncountable.
Like Cantor said.
Well, yeah, it could be the Cantor set. But for example, we know if we have f, there exists functions f which go from 0, 1 into R, which are continuous and actually uniformly continuous. Of course, because compact domain, right? And f is nowhere differentiable. Has everyone seen such a function before? Nowhere differentiable continuous functions.
Absolute value functions?
It's related to absolute value function. The construction is actually quite simple. You start on 0, 1. There's 1, not 0. You start with basically this function. You can write down what the formula for this function is. Call this phi. And then what you do is call phi k is phi of x over 2 to the k so phi k, what did I just do? Phi 1, for example, would be this function, right? But then you extend it periodically like this.
Mm-hmm.
And that's still a continuous function.
Yes.
And then you do f is the summation k equals 0. So this is phi 0 to infinity 1 over 2 to the k phi k of x. Since phi k of x is always less than 1, this sum converges uniformly.
Mm-hmm.
Right? You can use the Weierstrass M test.
Mm-hmm.
So it's uniformly convergent, and that means it's the limit is a uniform limit of a continuous function. So it's a uniformly continuous function.
Mm-hmm.
Continuous function defined on a compact interval, therefore it's uniformly convergent.
Yes.
And then you can check that the limit f of x plus h minus f of x h to 0, I'm sorry,
Mm-hmm.
does not exist for any x. If you want to know more about this, you can read
Chapter 1.
no, it's not in chapter 1. It's in Muncre's topology text has it in there. They do. Some were further down, but it's its own section, so you can find it out from the index where it is.
Mm-hmm.
Professor, the theorem 3.4
Yes.
use the same of this, yes? Page 121.
Yeah, 121. Well, the proof of theorem 3.4, which you haven't gone through, is, well, we use the definition of differentiability to show that if you have a bounded variation function, then it's almost everywhere differentiable.
Mm-hmm.
Any questions about the sunrise lemma or rising
Yes.
sun lemma?
There's so many questions, Professor. So on the page 121, right below that inequality, if G is non-empty, then it must be open.
Open, yeah.
Why is it why is it must be open? Is it because of that theorem 1.3 in chapter 1?
No, it's because of something very elementary.
Yeah, I thought so.
So this is G is continuous,
Yes.
right?
Yes.
So if I, for any fixed age,
Mm-hmm.
the set of all x such that this is greater than 0. This is open,
Mhm.
right? And the set E is the union over AH. Let me call this EH of the EH. Union of open sets is open.
EH. So why EH is open?
Why is AH open?
Yes.
Because G is a continuous function.
Uh-huh.
And so G of x
pre-image.
plus H minus G of x is also a continuous function.
Uh-huh.
It's the
Oh.
inverse image of the open set 0 to infinity.
Oh yeah, that's right. 0 to infinity, that's right. Okay. Inverse image. Okay.
So it's open, and then you take the union of all of them.
Okay, sure. Okay.
And so therefore is
Is open. Okay. Next question. In the
so
first paragraph of the proof,
yeah.
they say if AK, BK denote the finite interval in the decomposition, then AK is not in E.
Correct.
So why is it not why is it not in E?
Because it's an open interval, right? The
Uh-huh.
endpoints of an open interval belong to the open interval.
Oh, so it doesn't contain the endpoints?
Yeah,
Hmm.
because they are open intervals.
Okay. And E is set of open intervals. So and
union of
then and they're disjoint.
They are disjoint, and that's something.
Okay.
It goes back to chapter 1. If you have any open
Uh-huh.
subset of the real line, it has to be a couple disjoint union of open intervals.
Yes, that's right. Same goes with BKs.
The BKs are also not in there now.
Right. Okay, and then by the continuity, there's a C prime between D and BK.
Mm-hmm.
Why is G of C prime equal to G of C on the very bottom line?
Useless.
Hello?
Yeah, I'm reading that.
Oh yeah, yes.
G of D is greater than G of C.
Mm-hmm.
A C prime that's the intermediate value theorem.
Oh, okay.
You have G of D. G of D is greater than G of C.
Uh-huh.
And D greater C.
Mm-hmm.
That implies there exists a C prime
Bigger than D.
bigger than D and less than BK.
Mm-hmm. No, C prime is bigger than D, and then C prime is less than BK.
Right.
So this part should be like here. Where did it go?
Yeah. BK less than C prime less than D.
This way, the other way.
Yeah.
Like that?
Mm-hmm. such that g of c prime well, this is less than g of bk, right? So
Because
that
she is mm,
equals g of c. So and which we assume that c is the farthest point to the right where this holds, where g of c is g of ak plus g of bk over 2.
Okay. So this is the application of the intermediate value theorem.
Yeah. So the
Okay.
intermediate value theorem makes this work.
Okay. On the next page, page
Yes.
122.
Mm-hmm.
So this contradiction, GC prime is equal to GC, shows that we must have G of AK equal to G of BK.
Yeah.
So why they must be equal?
Why they must be equal? First of all, G of BK greater than G of AK can't happen, right?
Right.
Can't happen because otherwise BK would be in E.
Mm-hmm.
And therefore, right, but BK is not in E because it's an endpoint of one of those open intervals.
Oh, okay.
And the second argument will, they start with assume G of BK is less than G of AK, right?
Right. And then there's a contradiction.
They get a contradiction. Yeah. So if this is not true, if it's not greater than G of AK and it's not less than G of AK, the only other possibility, a famous result early on saying that
they must be the same.
in a linear ordered space, in a linear ordered set, linearly ordered set, that one of those three must hold and the first two do not hold.
Yes, yes. I got lost in the detail.
Yeah.
Oh my goodness, there's so
But
many.
the picture explains it pretty well.
Yeah. Yes, yes.
If you look at the picture of the rising sun lemma, it explains it quite well.
Yes, yes.
Right?
So in the picture, right, the central valley.
Yeah.
The central valley has a little hump there.
Right.
So
doesn't make a difference.
Doesn't make difference, right?
Because if you look at this, what it says G of x plus h is greater than G of x for some h. And let me draw a picture here. So if you look at this value of x, which is the little hump, right? Then if you choose h large enough to get over here, then you have something bigger, right?
Right.
Just means that you can find an h where it's bigger.
Oh.
Right. So if you take g of x to be the sine curve, just sine of x, then at every point you can find an h where it's bigger, right?
Right.
Even here, you can find one over here forever. The only points where you can't find one are the maxima.
Mm.
So the E in this case is the union. Where are the maxima? At k pi over 2. I should have used the cosine. K plus 1 pi over 2,
Mhm.
where k goes from negative infinity to infinity. So the only points which are not in E are just the multiples, the k plus 2 pi over 2.
Mhm.
Just the odd multiples of pi over 2.
Yes. So, Professor, when we have like we collect the data points and then we get some like idea of a function where we do not know how high it's going to go up. Like for example, right under the sun, the curve went down.
Mm-hmm.
And then since there's no future data points, we don't know this
No,
the
we don't know that.
yeah,
Because if
so
the curve would turn up steeply again,
uh-huh.
right? Everything to the right of the bold part would still be in the set E.
I see. So having not enough information, then we get at least a conservative estimate of E.
Yeah, well, I mean,
Ah.
you need to know the entire function to get that set E. I mean, if east of that last valley is Mount Everest, everything will be in the shade.
Yeah.
Right.
Okay.
Right.
Fair enough. That's it for me.
Okay, good. Any other questions about the rising sun? Songs have been written about it by the animals.
Oh, there's a
Okay.
song about rising sun, Lemma?
No, it's about the house of the rising sun.
Oh, okay.
Okay, I'm gonna look at one of the exercises for
Yes.
last time and try to explain what's going on here. Okay, this is exercise number 2. So you have K delta is a family of kernels which satisfies the following. First, absolute value of K delta of X is less than or equal to some constant A times delta to the negative D. I'm going to say something about this in a second. Is less than or equal to, this is for all delta greater 0, some constant A times delta over absolute value X to the D plus 1, where D is the dimension. And then the third condition is the integral from minus infinity to plus infinity, K delta of X dx is equal to 0. So obviously D is equal to 1. If K delta satisfies all these 3 conditions, then it has to be a function of the real line, right? Otherwise, the third one wouldn't make sense.
Oh.
Right. So the
Right.
D is 1. That's the first.
Okay.
That's the first thing we can do.
Sure.
And the claim is that f convolved with k delta of x converges to 0 almost everywhere as delta goes to 0.
Mhm.
So here is the idea of how to prove this.
Okay.
Idea of proof. Okay. First, it suffices to show this. If f is the characteristic function of some interval. Why is that the case? After all, what we're looking at, the convolution is an integral. Integration is linear. If we can show it for the characteristic function of some interval, we can show it for any simple function. So if we can show it for this implies it holds for step functions or simple functions. Which are dense in L1 of R. We wrote it this way, right? L sub 1 of R.
Yes.
Okay, so characteristic functions are sufficient, right?
Okay.
Everyone agrees with that? Because the
Yes.
rest comes from density argument.
Okay.
Okay. Now, how do we show it? So, and only for one interval, so I make my interval AB just the interval -1, 1. Right? Just for simplicity. Okay, so what we have to do is we have to look at the integral from -infinity to +infinity. Of x minus y times k delta of y
GY.
dy. This in absolute value goes to 0 as delta goes to 0. Okay, this integral we can write as the integral from, well, x minus y greater than -1. That means y greater than x minus 1. And less than x plus 1, k delta of y dy, right? Okay, so depending on what x is, first we assume that x is not equal to either plus or minus 1. Plus or minus 1 are no good. Because if x is 1, the integral goes from 0 to 2. And if it's -1, it goes from -2 to 0. And I mean, 0 is just on the edge of the interval. We don't want to have that happen. But that's only 2 points. We only want to show almost everywhere.
Okay.
Right? 2 points are we can throw away, no problem. So if the absolute value x is strictly greater 1, and the picture is the following. Here's 0, and the graph of this function looks like this. This is x minus 1, x plus 1. Right? Then if you choose your delta small enough, namely less than x minus 1, it's, if x is negative, the picture looks the same, it's just reflected. Then you can put two pieces. Well, you don't have to. Integral from x minus 1, x 1, k delta of y dy in absolute value is less than or equal to integral absolute value of k delta of y dy from x minus 1 to x plus 1. And this is less than or equal to a times delta times integral x minus 1 to x plus 1, 1 over absolute value x squared dx. And now you can evaluate this integral. This happens to be a times delta times 1 over x squared minus 1 if you compute that. That's just a little bit of calculus. And as delta goes to 0, this expression goes to 0 as delta goes to 0.
Yes.
Okay, now we have to only look at one other case. Actually, two more cases. Okay, next case. Actually, it is just one case. You have the origin here, and you have this situation, x minus 1, x plus 1, right? And then you choose delta small enough. Well, let me not choose delta yet. Then you can choose an epsilon. Choose an epsilon greater 0 such that an epsilon neighborhood of 0 is entirely contained in the region
Okay.
right. And now here comes the trick. The integral from x minus 1 to x plus 1, k delta of x, k delta of y dy is equal to the integral from x minus 1 to negative epsilon plus the integral from negative epsilon to plus epsilon plus the integral from epsilon to x plus 1. Right? Now what you do is, this open interval doesn't have to be symmetric, right? So you stretch out, you let epsilon, negative epsilon go to x minus 1, plus epsilon go to x plus 1. And so this is just the, becomes just that interval, x minus 1 and x plus 1 not included. And now we look at the absolute value of this thing. Let me just, k delta of y, and this is now less than or equal. Actually, I don't want to do that. Let me cancel that. So what happens with these kernels is, just draw here. That like this for 1, for delta equals 1, delta equals 1/2, what happens is that the graph will get compressed. So this will be closer together, right?
Oh.
Right? And the smaller delta gets, the more together is the graph, right?
Mm.
And so the integral from x minus 1 to x plus 1, which contains 0, k delta of x dx, goes to the integral from minus infinity to plus infinity, because everything is in the graph here, in the k1 of x, which is 0. Because everything is, if you make delta small enough, everything important is in that interval from x minus 1 to x plus 1, and outside it's just a very small value.
Mm. Okay.
Okay, and that shows, that's the sketch of problem number 2. Okay.
And then you said problem number 3. Oh no, you did problem
3 we did number.
Yeah.
We did number 3.
Yes.
We did number 3.
Yes, we did.
So the reading will be corollary 3.6, page 122, through page 127, where it says absolutely continuous function.
Okay.
And then I have the following exercises. Number 11. Number 12. And number 13.
Oi. Okay.
And any other questions?
No, thanks, Professor. Thank you.
So stay safe, wash your hands, stay away from me.
Oh, yes.
I don't know whether you've heard that little song by Randy Newman about social distancing. That's basically what he sings. Stay away, wash your hands, don't touch me.
Professor, can you recommend those crime novels you were talking about last time?
Oh, I'm right now reading a